of a classroom. A teacher does not start with the hardest real-world problems. Instead, they design simpler exercises that approximate reality, gradually transferring their understanding to the students. That intuition is exactly what knowledge distillation is about. In modern deep learning, we often train very large models. These models have enormous representational power, but they are expensive to deploy. They consume a lot of memory, require heavy computation, and are often impractical for edge devices, embedded systems, or latency critical applications. At the same time, these large models have learned very rich knowledge. The goal of knowledge distillation is to extract task-specific knowledge from a large model and transfer it into a smaller one without retraining everything from scratch. The key idea is this. The large model, called the teacher, already understands the world at a very high level. Here, it is defined as the cumbersome network. The smaller model, called the student or the distilled network, does not need to learn everything that the teacher knows. It only needs a relevant subset of that knowledge for a specific task. Consider an example. Suppose the teacher model is trained to recognize all animals: cats, dogs, birds, lions, everything. Now, we want a smaller model that only performs dog classification. Instead of collecting a massive new dataset and training a small model independently, we use the teacher's knowledge to guide the student. This guidance happens through a transfer dataset which can contain a small amount of labeled data and a large amount of unlabeled data. For the unlabeled data, we do something crucial. We pass the same inputs to both the teacher and the student. The teacher produces soft targets, not hard class labels. These soft targets come from a softmax function with the high temperature T. Why is this important? Because high temperature softmax outputs encode relative class similarities. They tell the student not just what is correct, but how the teacher views all classes in relation to each other. This makes the learning problem smoother and more informative. For labeled data, we still use the standard hard targets with temperature equal to 1. So the student learns from two signals. Hard target loss from ground truth labels, soft target loss from teacher's predictions. These two losses are combined using a weighted sum.